Good morning, everyone. Today I'm going to share RollPacker, our work on taming long-tail rollouts for reinforcement learning post-training with tail batching. This is a collaborative work with HKUST and Alibaba Group, and special thanks to Professor Wang for supervising this work. Reinforcement learning is widely adopted in LLM post-training these days, and leading LLM providers such as Queen, DeepSeek, Kimi, OpenAI, etc., they all rely on reinforcement learning to enforce their models with the power of reasoning or coding capabilities. And current RL systems aim to optimize the following workflow, which a typical RL post-training workflow consists of 3 stages: rollout, reward, and training. In rollout, the actor model actually generates responses from a batch of prompts. And these responses are evaluated in the reward stage. And in training, the model utilizes these evaluated reward signal to update their weights with algorithms like GRPO. This cycle repeats over steps. We profile the training time breakdown across different tasks of RLVR post-training workflows. As you can see, the rollout stage dominates over 60% of end-to-end training time across all tasks. And reward stage and training stage just take up the rest. So any significant speed up should address the rollout bottleneck. The response length of various task domains also follows a long-tail distribution. Say, most responses are short, but a part of small fraction of responses may have much longer length than the median. And this long-tail distribution actually causes GPU bubbles, as response may finish at different times. So for synchronous RL training, the rollout bubble appears at each step, which will actually result in low utilization and increased latency for synchronous RL training. Existing solution to improve its efficiency and tuck those bubbles falls into 2 categories. The first is stage overlap under synchronization constraints, which is to say, overlap rollout stage with a reward computation. But actually, as we mentioned before, reward computation typically takes for less than 15% of total end-to-end latency. So the gains are limited. And the second is relaxed synchronization, adopting a more aggressive asynchronous RL training as trade-offs to saturate GPU resources. While these approaches may compromise the on-policy RL training semantics and lead to degraded accuracy and stability. So since accuracy and efficiency are both important in RL post-training, we propose tail batching to balance between accuracy and efficiency. Our insight is quite simple. Only a small subset of long responses cause GPU bubbles. The max response length could be as large as 30 times larger than the median. So to exclude the impact of such long responses while effectively collecting valid batch for training, we borrowed the speculative execution philosophy from Spark. So instead of launching the exact required batch size, tail batching actually launched more additional, or you can see redundant prompts or requests, and we collect the fastest subset. So let's walk through the example. On the left figure, you can see the baseline GRPO, where we need 3 prompts, and each prompt generating 3 responses. And you can see long-tail distribution happens on both prompt level and response level, causing rollout bubbles. On the right side, you can see our speculative execution approach, where we launch additional prompts. Say, we launch 4 prompts, and each generating 4 responses in each step. So in this case, each prompt only collects the first 3 responses, and the whole batch collects the first 3 prompts. And the remaining are just aborted. So this is a race to completion strategy, which will naturally reduce the impact of long-tail distribution. However, simply excluding long prompts may cause problems because it distorts the training data distribution and may actually harm model performance. So in tail batching, we have to guarantee that no prompt should be permanently excluded. The aborted long prompts goes into a long prompt queue, which accumulate over steps. And when the long prompt queue collects enough prompt to form a batch independently, it triggers the rollout state of the next step with these prompts. In this case, when the long prompt queue gets 3 long prompts, the next rollout step will use these 3 long prompts to generate from scratch with a new LLM model. And in this round, each long prompt will generate only 3 responses, which means that tail batching will not invoke speculative execution in this round and tolerate the long tail distribution. This round is indeed considered as long round. So the full pattern of tail batching is quite clear now, which is several fast short rounds followed by 1 long round without speculative execution. So in this design, all prompts are eventually included in training, and each step only relies on the current model weights, which preserves on policy semantics. So it's natural to consider whether tail batching affects accuracy. As we just mentioned, tail batching only reorders short and long prompts. Every prompt is eventually included, and we ensure no previously generated responses from a still model will be used in later steps. And recent algorithmic works also reorder prompt for efficiency, indicating that reordering does not affect model accuracy. We also validate this across 7 billion, 14 billion, and 32 billion models against the world baseline. The blue line shows the validation score of each step of RollPacker using tail batching. The score proves that tail batching preserves training quality. Here, we show the efficiency gains. We compare the response length of tail batching with the world baseline. You can see the blue box indicating the response length distribution against world across multiple steps. And the first 4 steps are the short rounds, while the last step is a long round. You can see that tail batching yields consistently shorter and more balanced response lengths in short rounds. And since that the long prompts are deferred to the long round, in long round, tail batching have a slightly favor of longer responses due to this reordering. About training latency, we can see the figure on the right, showing that tail batching significantly reduces training time. And we have 2 observations here. The first one is, as the rollout time was accelerated, the reward state becomes more pronounced in the whole training pipeline. And the second one is, both short and long rounds still contribute substantially to the total latency. And these observations will motivate our further optimizations. But before that, let's first discuss the potential overhead of tail batching. As we can see, speculative execution introduced negligible latency costs. The time to first token and time per output token of long and short rounds remains identical. However, as we are launching additional redundant prompts and responses, the concurrent output tokens between long round and short rounds will be significantly different. We can see in the figure on the right, where the red line shows the concurrent tokens of short rounds. For example, like when we launch 1.25 times more responses and prompts, initially the concurrent rollout tokens of the short rounds get 1.6 times higher than that of the long round. Although it's dropping fast, indicating that the rollout stage was faster with speculative execution, the peak KV cache pressure of the short round is much larger than that of the long round. So this memory disparity further motivate our optimization of the parallel planner. We will introduce that in future slides. So here's the system overview and the workflow of RollPacker. During rollout, tail batching first decides whether to adopt speculative execution in each round. And parallelism planner uses either offline profiling data or online monitoring to decide the optimal parallelism config of each step. And the reward scheduler concurrently compute rewards with ongoing rollouts. So as rollout progresses, the stream trainer scales down idle rollout GPUs, reassigns them to training. So in this case, in this stage, the stream trainer only computes gradient from completed responses, and after the rollout stage finishes, it collects the computed gradients, renormalizes them, and triggers a weight update synchronously. So let's go through these optimizations step by step. The first one is paradigm planner. As we mentioned before, the short run have substantially higher KV cache pressure than the long run. So this indicates that the optimal tensor parallelism size may differ between short and long runs. Our proposed parallelism planner adopts an adaptive TP selection on a per-step basis. We first do offline profiling to configure the initial TP config. And with online execution, we collect the number of preemptions in each step and adjust TP size accordingly, whether halving or doubling based on the decrease or increase of the preemption count. This lightweight heuristic will adapt to changing workloads with negligible overhead. The second one, the reward scheduler. We also implement a reward scheduler with tailored optimizations for each task reward computation. Here, we take LLM as a judge as an example. Traditional RL systems reserves a fixed number of GPUs for the judge models exclusively. Well, it brings problems. These reserved GPUs have suffered from low utilization, about only 20%. So this indicates that the approach is inefficient. And in RollPacker, we tend to co-locate the judge model with the actor model on the rollout GPUs. And to reduce interference, we use MPS. And also, to save GPU memory for more precious KV cache, we implement a layer-wise pipeline to offload the judge model's weights to the CPU memory to reserve GPU memory. Consider that long runs still suffer from the long tail distribution as responses complete at different time without speculative execution. We propose a stream trainer to dynamically scale down rollout GPUs and reassign them for training. So it monitors the fraction of completed responses and decide when and which GPUs to scale down from rollout to training. The ongoing rollouts on these GPUs will be migrated to remaining instances and use a recomputation-based policy to restart, while the free GPUs are used for training. In this case, they asynchronously fetching the completed responses, compute their gradient, and buffer them. To keep the on-policy semantics, no model update is incurred in this time. And after the finish of the rollout stage, the stream trainer collects all the computed gradients, renormalize them based on the response count, and trigger a synchronous weight update for the next step. This method is mathematically equivalent to standard on-policy training. So we use a multitask RLVR workload to evaluate the performance of RollPacker. The cluster setup and hyperparameters are shown below. And we compare RollPacker with the world baseline and average views. We mainly focus on end-to-end training time. So for the end-to-end evaluation, the blue solid line here shows the step time of RollPacker among multiple steps throughout the training process. We can see that RollPacker achieves more than 2 times speed up over world and average views. So this speed up mainly favors longer responses length. As we can see, the gap is the largest for the 33 billion with 33K response length. So let's discuss the performance in more detail. In this table, we can see that tail batching is more pronounced for longer response length because with longer response length, the long tail distribution is more severe. Reward scheduler favors short rollouts, while it's still effective for long sequences. The parallelism planner, however, favors long ones with larger model size because it introduces more KV cache pressure. The stream trainer especially benefits well-balanced and rollout and training configs. In this case, it's like the Queen 2.5 14 billion model with the 16K response length scenario. For the step breakdown across model sizes, we can see that long rounds still suffer from, or still are dominated for the rollout stage. But the gain of RollPacker comes from the more frequent and faster short rounds, which will significantly reduce the overall average step time. Finally, scalability. We scale the batch size from 128 to 512, along with GPU resources. We compare with the world baseline, and we can see that RollPacker consistently outperforms worlds at each scale, indicating that RollPacker maintains performance at scale. To conclude, we propose tail batching, which can effectively mitigate the long tail effects while preserving the semantics of on-policy training. Our proposed parallelism planners, reverse scheduler, and stream trainer further capitalize these benefits of tail batching. And our experiments on multiple models and scales shows that RollPacker substantially reduces training time without affecting the model accuracy. And RollPacker is open sourced. The code is available on GitHub, and I'm happy to take any questions now.